So hello everyone, a very good evening to each and everyone out there, and I welcome you all to this amazing platform of PW Gulf. This is your math educator Shivangi Rajput, and in this particular lecture we are going to start with another chapter, that is our circles, and we are going to finish this chapter in one single video. So we are going to discuss about all the theorems, the basic concepts related to circles, what is an arc, segment, sector, all about it. So let's begin with our session for today. So basically, let's see that what is our topic to be covered today, what is our table of content for today. So we are going to start with the introduction, students. Then we are going to learn about what is the interior and exterior for a circle. After that, we are going to have a conversation about the arc, sector, segment, and most importantly, angle subtended by a chord at a point, some important theorems, perpendicular from the center. Then we need to understand about the angle subtended by the arc of a circle, and after that we are going to deal with some questions regarding the same topic. So these are all the topics that we are supposed to cover today, and all these topics will be covered in one single video, so it will be really helpful for you to understand the basic concepts of the chapter circle, because circle is a figure that you have studied since your junior classes, right? That it has no edges, no vertices, it is a simple curved closed figure, and then you learned about that it has a radius, a diameter, and all the other things. But now in this particular class 9, we are going to learn about the chords, the arc, the segment, the sectors, and all the other parts that are related to your circle. So let's start with the very first thing, that is the introduction to the chapter. So the very first thing that we know about this plane figure is that it is a simple curve, right? Circle is what? Nothing but a simple closed curve. Now this circle has a specific center, right? And from this center, any part which touches the boundary of the circle is known as the radius of the circle. This is what we have already learned, and this is what we are already aware about, right? Now when this radius is doubled, right, so this particular whole 9 is known as the diameter of the circle. So this is also something that we are already aware about. So these three things, that this is the center, from the center to the boundary is known as the radius of the circle, and then when this radius is doubled, or basically from one point on the boundary of the circle, if the line reaches the other part, going through the center of the circle, that is what known as the diameter of the circle. So these are the things that we are already aware about when we talk about circles, right? The next thing that we are going to learn over here is basically what is the circumference. So this boundary that we talk about, students, this boundary that we talk about of the circle leads to what? The circumference of the circle. So this is what known as the circumference of the circle, right? And the region enclosed by this particular circle is called the area to the circle. So these are all the introduction, the basic concept that we have already learned. Now let's move forward to the next part, that is the interior, exterior, and the third one is on the circle, right? So you just have to imagine a cricket stadium for that, right? So basically when we talk about the cricket stadium, just remember the boundary line, right, on which the ball just touches and it makes a 4 or a 6 or something like that, right? So basically when we talk about this green region, like for example, if I talk about that this particular line that I just made, right, this represent that border line, right, that border, that where it gets strike through, it is a 4 or a 6 or run whatsoever. So this is the border of the circle. So basically all the players are present inside this green circle, right? All the players are present inside the green circle. So this is known as interior of the circle. Got it? Now the rest of the people who just sits outside this boundary, that is, for example, in this particular region, that is in the stadium, to enjoy watching the match, right? They sit outside the boundary, right? And that is known as the exterior of the circle. And certain time it happens too that if this is the particular ground and if there are the people who are playing inside, and for example the batsman hit and the ball just strikes over your boundary line. That makes us 6. That means on the circle. So from this what we can say is that a circle comprises of 3 particular regions. And what are these 3 regions? One is known as the interior of the circle, where all the batsmen and bowlers are present along with umpire and rest of the people. Then outside the circle, where basically we people, that is the people who go to watch the match, they sit exterior of the circle, and the boundary line itself is known as on the circle. So basically whenever we draw a circle on a plain page that we have, students, so that circle divides that plain page into 3 parts, that is the exterior of the circle, on the circle and the interior of the circle. So these 3 are the things that our plane is divided into when a circle is drawn on it. Let's see the next thing that we have is arc of the circle, right? Let's talk about the arc. If this is the circle, students, that we are talking about, right? So basically from its circumference, if I take a part of its circumference, that forms an arc of the circle. If for example I choose this part, right? For example, if in this I choose a part from here to here, that is this part. So this yellow part will become the arc of the circle. Now you might have this question, ma'am, is only this yellow part becomes the arc, or this remaining pink part also is an arc? So students, yes, this remaining pink arc is also an arc. So this yellow arc, comparatively small, right? So this is over here known as the minor arc. And this pink arc over here, which is more in quantity, which is lengthier, which is of greater length, so this is known as the major arc. So minor arc, the smaller one, major arc, the bigger one. I hope this part is clear with everyone about the arc. Arc is nothing but just a part of the circumference of the circle that we take. Now let's move forward to the next thing and understand a sector. Now this slides give us a bit of hunger strike, right? So basically what is sector? Just when you talk about sector, imagine a slice of pizza. That is it, nothing else. So you know that pizza is nothing but a circular thing, and that circular thing is divided into 4, 6 or 8 whatsoever part depending on what size you have ordered, right? So now in this particular thing, basically when the pizza is divided into smaller slices, and those smaller slices now then can be categorized. So one slice, if we take out this one slice, this is nothing but is of a shape of a sector of a circle, right? So this is what is formed of. So basically this is the radii of the circle, right? This is the radii of the circle, and this is the arc of the circle, students. What I am telling you, radii and arc of the circle. So now when we talk about what is sector, so sector is a part of a circle that is formed by 2 radii and an arc of the circle. Now let me draw it again. So basically what I told you, people, that if this is the pizza that we are ordering, right, and what we did, we just cut it into slices. We have just cut it into slices, right? Alright, now if I talk about this particular part, so this becomes a sector of a circle. This is also a sector of a circle. This is also, every slice is a sector of a circle. And not only every slice, students, when we pick up one slice, or if I talk about, let's say I just cut this into one simple slice, right? So this is formed by radii and arc of the circle. But if you will think on the bigger picture, right? So this is the radius, and this is also the arc of the circle. So again, students, if we talk about sector does not always means a smaller slice, right? After removing this smaller size, for whatever pizza is left, this also forms a sector of a circle, because this is also comprised of radius and the major arc. So similarly, we can categorize the sectors as this is the smaller one. So this is known as the minor sector, students. And since it is the bigger one, so this is known as the major arc. Right? So minor arc and minor sector and major sector, sector. Right? So this is the minor sector and this is the major sector. So when we talk about these two, so it's not only one slice, it is the rest of the slice too. You just have to see that that particular thing is made up of two radii and one arc of the circle, and that arc can be the major arc, can be the minor arc as well. So this is what about a sector means. Now the next part that we are going to learn is about the segment, right? So since we have learned about the sector part, so this is the minor sector, this is the major sector. Now when we talk about the segment is nothing but just a chord separating two regions in a circle. Now what is a chord, students? From one circumference, from any point in the circumference of the circle, if the line touches the other part on any part of the circumference of the circle, that forms a chord. Right? So if we talk about a chord, students, if this is the circle that we are talking about, so this can be a chord, this can be a chord, this can be a chord, and the diameter is also a chord, and given that diameter is the longest chord of the circle. So this is what we have to deal with, right? So basically any line which starts from the circumference of the circle and ends at the circumference of the circle, so it forms the chord of a circle. So now such region which is separated by chord, so the greater region is the major segment, the smaller one is the minor segment. When we talk about sector, students, sector is comprised of radii and arc. When we talk about segment, the segment is only comprised of chord and arc. Sector, radius and arc, segment, chord and arc. Right? I hope the difference is clear between sector and segment. Let's do some quick fill in the blanks, students. Let's see what's there on the fill in the blanks. So the longest chord of a circle is the dash of a circle. So we have just discussed this, that the longest chord of the circle is a diameter of the circle. Right? So any diameter that you draw for that circle will be the longest chord for that circle. The next, an arc is a dash when its ends are at the ends of a diameter. So just imagine this, we have a circle, right? Arc is what? The part of the circumference. For example, we made a diameter. So what is it saying? That starting from here, this arc and ending, the ends are at the ends of diameter. So that is what is known as, this is what is known as the arc of the circle, and this forms the semicircle, right? So arc is what? Arc is a semicircle when its ends are the ends of diameter. Segment of a circle is the region between the arc and, so when we talk about the segment, students, if this is a circle, so this is segment. So segment is formed between arc and chord of a circle. C-H-O-R-D, chord of a circle. Now next, a circle divides the plane on which it lies in dash parts. So we have learnt it in the very starting in 3 parts, and those 3 parts are interior, exterior and on the circle. Next is true and false. Line segment joining the center to any point of the circle is the radius of the circle. So line segment joining the center to any point on the circle is the radius of the circle. Yes, from the center to any part on the circle. So this is what your true statement. The next thing that we have is a circle has only finite number of chords. Not at all, students. If this is your circle, you can draw n number of chords, right? N number of chords can be drawn. So no, it has infinite. It has infinite number of chords. The circle can have infinite number of chords when it comes to it. The next we have is, if a circle is divided into 3 equal arcs, each is a major arc. So basically what is it saying? That if we have a circle and if circle is divided into 3 equal arc, right? For example, this arc and this arc. Let's say that this arc is equivalent to this arc and is equivalent to, for example, this arc. So each is a major arc? No, each one is a minor arc, right? Because this part is the least part of the arc, you can say, or you cannot say that this is the major one, right? So this will become what? A false statement. The next thing that we have is a chord of a circle which is twice as long as its radius is the diameter of a circle. That's true. So when we double the diameter, when we double the radius, it becomes the diameter of the circle. Alright, now let's learn about the angle subtended by a chord at a point. So basically students, let's see that if, for example, this is a circle. Right, for this circle, let us assume that this is a chord. Let's name this chord AB. And this is, for example, say the center of the circle. Now, what I want to tell you people is that when this chord is made, right, as you can clearly see that it divides the circle into 2 segments. One is the major segment, the other one is the minor segment. So when a chord is drawn, a circle is particularly divided into 2 segments. One is the major segment, the other one is the minor segment. So basically this chord can subtend 3 different angles. We are already aware about, and we can have this thinking that the major segment will always have a center. Right, because the major one always includes the center. So in the major segment, 2 angles can be drawn via this chord, and in the minor segment, 1 angle can be drawn. For example, if this is the chord, at the center, it can subtend this angle, students. Right. The other angle which this chord can subtend is this angle. And the third angle, students, which this chord can subtend in the minor segment is this one. Right? So what we have seen over here is when a chord is drawn, so that particular chord can subtend 3 different angles. So 2 angles in the major segment. Right, this becomes what? This becomes the major segment. So basically this chord can subtend 2 angles in the major segment, one at the center and other in the remaining part. The third one that we have is in the minor segment. Right, this is in the minor segment and this is where it comes. So basically when we talk about chord, a chord can subtend 3 different angles in a particular circle. I hope that this thing is clear with everyone. Let's move forward. So from here this theorem 1 comes into play, which says equal chords of a circle subtend equal angles at the center. Now what does it mean, students? For example, it is given that AB and CD are 2 different chords for this circle. Right? What can we say? What can we say over here? That AB is equals to CD. That is given in the question. What we have to prove in this theorem, that angle AOB, we have to prove that angle AOB is equal to angle COD. This is something that we have to prove. Now, what is in this part, students? What do we have to tell? See, first of all, we will join AO, BO, CO and DO. Now, what can we say? See, we can say the very first thing as AO is equals to CO. We can say that BO is equals to DO. Why we can say that? Because these are radii of the same circle. And if they are the radii of the same circle, that means they have to be equal. We can say that angle AOB is equivalent to angle COD as they are vertically opposite angles. So what can we say? That triangle AOB is congruent to triangle COD by what we can say? We can clearly say, sorry. No, the third thing that we will be taking is that is given to us AB is equals to CD. Sorry, AB is equals to CD, that is given to us. These are not vertically opposite. This is what given to us. So what we can say that by triple S congruency criteria, by SSS congruency criteria, we can say that these two triangles are congruent, and then we can say that angle AOB is equal to angle COD by CPCT, that is corresponding parts of congruent triangles. So as simple as that. So basically, what is the meaning of theorem that we have to keep in mind? So we have to keep in mind that if a circle is drawn, students, and if for example one chord is equals to other chord and this is the center, we are given that this is equals to this. Now what we can say that the angle subtended by these two chords at the center will be equal to each other. The next theorem that we have is, if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. Now this is the converse of the previous theorem, and what does it states? For example, you have a circle, students, and it is given that there are two chords. Right? It is given that there are two chords, but it is not given that they are equal. It is just given that here are two chords, but it is not given to you that these two chords are equal to each other. Now basically what you have to do, these two chords subtend certain angle at the center. Now what is given to you is this angle is equal to this angle. Right? So if two chords are given to you, and also it is not given that they are equal in lengths, but it is given that they subtend equal angles at the center, so you can clearly say that these two chords are equal. How we can prove? Over here in this question, see, if this is O, this is A, this is B, this is C, and this is D. Again, we can say that AO is equals to OC or whatsoever. We can say that AO is equals to OC, we can say that BO is equals to OD, and now we can say that angle AOB is equals to angle COD. Why? Because it is given to us, and these two because these are the radii of the circle. So we can say triangle AOB is congruent to triangle COD. Right? And if the triangles are congruent, so we can say that AB is equals to CD by CPCT, that is the corresponding parts of your congruent triangles. I hope this thing is clear with everyone. Let's see perpendicular from the center to a chord. Let's learn about it. Now, what does perpendicular from the center of the chord means, right? So, for example, students, we have a circle, right? For example, we have a circle and we also have a chord. Now, basically, this is the center of the circle. And perpendicular word means what? Perpendicular word means 90 degree. That means from the center, a very straight line is drawn that is perpendicular to your chord. Now, what are its relationship? Let's learn about it. So, the very first thing says is the perpendicular from the center of a circle to a chord bisects the chord. What does it mean? Listen to me. So, if you have a circle and if you have a chord and from the center of a circle you draw a perpendicular. So, this perpendicular will divide this chord into two equal parts. Let's take an example. For example, you have a circle, students. You have a chord and this chord is of 8 centimeter. Right? Now, from the center, a perpendicular is drawn. Now, from the center, a perpendicular is drawn. Right? So, basically, at the point of perpendicular, this line will be divided into two equal parts. Now, what's the proof for this? See, join this and this. Let this be A, let this be B, C, and D. Now, you can see two triangles ABD and ACD. right? You can see two triangles, that is ABD and your triangle ACD. Let me mark these two triangles for you people. One triangle is this one and the other triangle is this one. So these are the two triangles that we are talking about in this particular figure. Now basically what we have to do, we have to prove that congruency again. So first of all, we can say that AB is equals to AC. Why AB is equals to AC? Because these are again the radii of the circle. The second thing that we have is AD is equals to AD, students. Why? Because this AD side is common in both the triangles. And third thing, since we have drawn a perpendicular, that is a 90 degree, so we can say that angle ADB is equals to angle ADC 90 degree each. So now the major part comes, that what congruency. So certain people do SAS congruency, that is wrong. So we have taken a right angle. By RHS congruency, the triangles become congruent and we can say that BD is equals to CD by CPCT. So we can say that when a perpendicular is drawn to the chord, that bisects the chord into two equal parts. Let's move forward. Theorem 4 says the line drawn through the center of a circle to bisect the chord is perpendicular to the chord. Now this is the converse of the theorem 4 that we have already learned. So it says that if there is a chord and from the center a line is drawn, now it is not given to us that the line is perpendicular, but it is given that this part is equivalent to this part, right? So now again we have to join this and this. Again we have to prove congruency in these two triangles. Radii equal to radii, side is common and this third side is equals to this third side as it is already given in the theorem. So we can say that yes, these two triangles are what? Congruent. Then we can say what? That this angle plus this angle will be 180. First of all, both these angles will be equal. Why? By CPCT. Over here, see, this angle will be equal to this angle by CPCT. And we also know that sum of these two will be 180 as these are forming linear pair. Adjacent angles, linear pair. Right? So basically now we can say that each will be 90 degree, that is perpendicular. Let's move to theorem 5. There is only one and only one circle passing through three given non-collinear points. Now let us first understand what are these non-collinear points, students. Right? So when we talk about non-collinear, see, collinear means 3 points are coming on a same straight line. That means if I draw 3 particular points and if a straight line can pass through these 3 points, so such 3 points are known as collinear. But of course, it is very understandable that no circle can pass through 3 non-collinear points. Right, sorry, 3 collinear points. But now if we have 3 non-collinear points, that is one here, second here and third here. As we can clearly see that these 3 points are not falling on a same straight line. So what we can say that there is one and only one circle that passes through such 3 given non-collinear points. Only one circle can pass through it. So there is one and only one circle passing through 3 given non-collinear points. The next thing that we have is equal chords of a circle are equidistant from the center. Now what does this mean, students? What does this mean? Let's understand this, right? Alright, let's make 2 circles, one here and the other here. Now what does it say? Equal chords of a circle, right? For example, these 2 circles are equal to each other and let's say these are 2 equal chords. For example, AB is equals to CD. Now if this is the center, this line, if this is the center, this line. So what I am telling you, student, is that if the chords are given, that the chords are equal, so the distance So the distance, which distance, students? This distance from the center to the chord, from the center to the chord, right? So this distance will be equal as well. If this is O, this is D, if this is for example E and F. So we can say that if AB is equal to CD, so we can say this implies that OD is equals to EF. Also, if these two chords are present in a same circle, for example, this is the circle, this is one chord, let's say AB, and this is another chord, let's say CD, and it is given that AB is equals to CD, and if this is the center of the circle, students, so we can say that this distance and this distance will also be equal to each other, right? So this is what theorem 6 means. The next theorem that we have is chords equidistant from the center of a circle are equivalent. Just the converse of the previous theorem that we have already learned, that if the chords are equidistant from the center, then they are equal. The earlier theorem stated that if the chords are equal, they are equidistant. This, if they are equidistant, they are equal. I hope this is clear. Two equal chords of a circle intersect within the circle. What is it saying? If two equal chords of a circle intersect within the circle, prove that the segment of one chord are equal to the corresponding segment of other chord. We have to prove that the segments are equal. Now, how to do this? See, if two equal chords of a circle intersect within the circle, we have chords, right? And those two chords are intersecting within the circle, right? For example, like this, they are intersecting at one specific point. Prove that the segment of one chord are equal to the corresponding segment of other chord. See, if the chords are equal, students, so that is very specific that the segment which they are having are also equal, right? Let's move forward to the next part. Now, let's see this question. Over here it says, if a line intersects, right? So, it says that if a line intersects two concentric circles with the same center, with center O at A, B, C and D, prove that AB is equals to CD. The very first thing that we can do is from O, draw the perpendicular, right? Now, let's talk about the small circle, right? Let's talk about the small circle. So, in small circle, we can say that, for example, let's name this as P. We can say that BP is equals to CP. Why? Perpendicular from center of circle bisect. I hope you guys remember this. Perpendicular from the center of the circle bisects the chord. Now, in the bigger circle, students, again we can do the same thing. That means AP is equals to DP, right? The reason is same, that the perpendicular from the center of the circle bisects the chord. That's why they are equal. Now, let's say this is the first equation and this is the second equation. Now, the third step is simple. From the second equation, subtract the first one. That means AP minus BP should be equals to DP minus CP. So, from this we will get that AB is equals to CD. I hope this part is clear with everyone, right? Let's move to the next question. Now, angle subtended by an arc of the circle. This is as equal to as the chord of a circle. Let's understand this point. Again, when we have a circle, right? So, this circle, if I take an arc like from here, let's take an arc to here. This is the minor arc, right? So, basically, if this is the center of the circle, so this particular arc can again subtend three particular angles. One is at the center, the other one is over here in the remaining part, and the third one in the down part, right? So, we have a relationship between these three angles. Let's learn about them. Theorem 8 says that the angle subtended by an arc at the center is double the angle subtended by it at any point in the remaining circle. Now, what does this mean? Let's understand this. For example, we have a circle. and from here to here, this is the arc that we are taking, and this is the center. So what I'm telling you guys is that if this arc subtends this angle at the center and this angle in the remaining part of the same segment, so whatever angle is made here, for example, the angle over here is 100. So this angle is double than this angle. That means this has to be 50. So if this is 50, this is 100. If this is 10, this is 20. If this is 150, this is 300. That means the angle at the center is double as compared to angle in the remaining part of the circle. And students, when I talk about the remaining part of the circle, that doesn't only mean this angle. It can also be this angle. It just have to start from this arc and end at this arc. All these angles are same, right? It's not only one angle. See, only one angle can be made at the center, but when we talk about in the remaining part of that segment, so multiple angles can be formed, like this can be formed, this can be formed, this can be formed. So multiple angles can be formed. I hope this part is clear with everyone, right? Let's move forward to the next. Now this part says that the sum of either pair of opposite angles in a cyclic quadrilateral is 180. Now, what is a cyclic quadrilateral, students? So, a cyclic quadrilateral is a quadrilateral whose all 4 points lie on the circumference of the circle. For example, if this is a circle, this is point 1, point 2, point 3, point 4. If I join this, since all the 4 points of this quadrilateral are lying on the circle, so such a quadrilateral is called a cyclic quadrilateral, and the opposite angles, this angle and this angle, will give you a sum of 180 degree, and this angle will give you a sum of 180 degree. So this is how we find it out. I hope this thing is clear with everyone, right? Let's move forward. Now let's see the question. In figure given below, A, B and C are 3 points on a circle with center O. If BOC is 30, students, this angle is 60. Then we have to find angle ADC. Now again we have to use the theorem. It is very simple question. See, what we can say is angle AOC is equals to what? 90 degree. 60 plus 30, 90 degree. What will be angle ADC? Angle ADC will be equal to half of angle AOC. Why, students? Because this is angle subtended by arc at the center. Subtended by the arc at the center. So this has to be half of it. So since we can say that ADC is half of AOC, that means half of 90 degree, which is equals to 45 degrees. So what we can say that angle ADC is equivalent to what? Is equivalent to 45 degree. Let's move forward. This says a chord of a circle is equal to the radius of the circle. What does this question says? That we have a figure and the chord of a circle is equal to the radius of the circle. Alright, let's say for example, if this is R and if this is a chord, this is also of the length R. So find the angle subtended by the chord at a point on the minor arc and also at the point of the major arc. So we have to find the angle subtended by the chord at the point on a minor arc and also at the point of a major arc. See, for example, if I draw it like this, so this is also equivalent to radius. So what you have to find out, did the angle subtended by this particular figure, particular chord in this arc and in this arc. As we can see that all the 4 points, right, all the 4 points basically formed are on the circle. So what we can say that angle subtended over here and the angle subtended over here, for example, both will give you a sum of 180 degree and both will be supplementary angles, and what are their individual count? This is something that you guys will tell me in the comment section, right? So the addition of these two will be 180, that is for sure, because all the 4 points are lying on the circle. It forms a cyclic quadrilateral. But what will be the exact angles? Just comment it down, right? Next question. Over here it says if PQR is 100, so we have to find OPR. This small angle. See, first of all, just look at the figure. This is the circle, right? This is O, P and R, and over here this is 100. You cannot say that this is cyclic quadrilateral. Why? Because O is not lying on the circle. It is the center of the circle. So since student, if this is given as 100, right, this is the angle in the segment. So if you are making the angle at the center, so this will be double. That means if this is 100, so this will be 200 degrees. Now look at the different picture. See, now since you have got this as the center, this angle as 200, and now you have this, that is P and R. If this is 200 students, so this will be 160. Angle around a point is 360 degree. If this is 200, this has to be 160. And if this is 160 students, so just apply angle sum property of triangle in this small triangle. If this is 160, this side will be equal to this side. Why? Because both of them are the radii of the circle. So OP will be equals to OR. Why, students? Because it is the radii of the circle. So if this is 160, this is equals to this. So each of them will be 10 degrees, so that they add up to 180 degrees. The next thing that we have is, we have to find BDC, that is this angle, students. See, very simple. Over here, first focus on this triangle, right? See, if this is 69, this is 31. So by angle sum property, this will be equals to 180 degree minus 69 plus 31. That is 180 degrees minus 100 degrees, sorry. Right? So this will give us 80 degree. If angle this is 80 degree, so we can say that angle BAC will be equal to angle BDC. And why we can say that? Because these are angles in the same segment, and angles in the same segment are equal. So angle BDC will also be 80 degrees. I hope this thing is clear with everyone. The next question over here says is find BAC. So we have to find this particular smaller angle. See, just look at the figure. From the figure only we will be solving these easy peasy questions, right? We just have to focus on the figure. See this part. If this is 130 students, this will be equivalent to 50 degree, right? Linear pair. If this is 50, this is 20, this will be equivalent to what? 50 and 20, 70, 110 degree. If this is 110, so this will also be 110, because these are angles in the same segment. As simple as that. So this was all about the chapter, students. It's an easy peasy chapter, and you just have to focus on the theorem, understand it conceptually and basic. If you have any doubts, please do comment it down, and that homework question too. So I'll see you guys in the very next one shot explanation of another chapter. Till then, take care. Have a great time ahead. Thank you so much.